All right, Chapter 9, Section 6, Solving Right Triangles. The very name of this section is going to be the culminating experience of Chapter 9 on right triangles and trigonometry. Basically, we're going to be getting minimal information about a right triangle and then using that information to start fitting in the other pieces and solving the entire thing, all three side lengths, all three angles on the inside. It's going to be using a lot of the previous concepts that we've used up until this point. We'll be using everything from triangle sum theorem, adding up the angles inside the triangle. We'll be using Pythagorean theorem at the beginning of this chapter, a squared plus b squared equals c squared. And then we'll also be using our trig functions, sine, cosine, and tangent, that the last couple sections have been focused around. All of these things are going to kind of culminate in this experience, and we'll be seeing it used as a whole. To start this lesson, though, we want to learn about the inverse of the trigonometric ratio. And so each of our trig ratios, sine, cosine, and tangent, as with any math operation for that matter, has an inverse, basically a way to undo it. And you'll be familiar with many of them. Up until this point, you'll be familiar that addition and subtraction are inverses of each other. If I'm going to add two things together, I could undo it or reverse it by subtracting them. If I multiply two things together, I could divide them, be the inverse operation. And then just moving forward, the little more complicated ones like the square root, to undo the square root would be this to square it, and vice versa. All of these operations that we've learned up until this point have some way to undo them. The same goes for the functions that we've explored in the last couple sections, namely the sine, cosine, and tangent. Basically, a way to undo what has been done. Okay, this is a basic requirement of a math operation. If I do something, I should be able to undo it and get back to where I began. So, how can the inverse trig ratios be used? Well, as you plainly see here in the definition, inverse trig ratios are used to solve angle measurements. So in section 4 and section 5 that explored the sine, cosine, and tangent, taking the sine, cosine, or tangent of an angle resulted in the ratio, the scaled factor ratio of two sides of a right triangle, and which two sides depended on which trig function was applied to a given angle. Sine being opposite over hypotenuse, cosine being adjacent over hypotenuse, and tangent being opposite over adjacent. And you get these resulting ratios. And again, this part over here on the left is essentially what we explored in the past several sections. This is just kind of the summary of that. So what does an inverse trig ratio do? So essentially what is happening here, going from the left to the right. So for instance, for the sine of angle A specifically, sine of anything, again, for SOHCAHTOA, sine for the SO is going to be opposite over hypotenuse. There's the O and the H. Okay. And so the sine of some angle A will be the opposite side of angle A over the hypotenuse of this triangle. And in this instance, that would be the side X over here over Z. That's what we learned in section 5 when we explored the sine function. But if I were to say, move this sine, the sine function to the other side of the equation, thus leaving just angle A behind, this is what happens. That angle A is now by itself over here on the left. And the reason I put this measurement of angle A is that when I do this in a calculator, and rest assured, this is nice. This is a function, an operation in your calculator. So it may look scary, but this is, again, just kind of a series of buttons to be pushed on a calculator. But whatever happens over here, the results, whatever happens on this side of this crazy equation, the result is going to be some degree measurement of an angle. And this is really one of the more useful ways that trig ratios are used. Often in real life, in the physical world, it's a lot easier to measure a distance, like say a side of a triangle, to know a distance or to measure a distance than it is to measure an angle measurement. And these angle measurements can become very valuable for figuring out how far like a bridge has to be elevated or some support system. As I said, in engineering and construction, right triangles and trig ratios are used all the time. And as with most of these things, it's a lot easier to measure out like, okay, let me figure out a height or a width or a length of a given measurement for a steel beam or for a pulley system than it is to measure an angle. And so the inverse trig ratios, well, be what we use to solve for that angle. So again, kind of the punchline here is that an inverse trig ratio, in other words, we're going to see this -1 sign. This is a sign of an inverse of something. Essentially, it's doing the opposite of what sine does. So sine, again, tells me the ratio of two side lengths. So this is, again, just a ratio of side lengths. Whereas the inverse sign of something will tell me in degree measurement of a given angle. In this case, angle A. Okay, so when would this be used? When would these be used? These inverse trig ratios are used when I happen to know the two side lengths that I'm comparing, whether they be the opposite hypotenuse or adjacent hypotenuse or opposite adjacent. If I know the two side lengths explicitly, I can use that information basically to backtrack and figure out what angle is going to force that ratio. That is the use and function of the sine, cosine, and tangent inverse. So just to briefly show you on a calculator, again, on my calculator at least, you'll see that there's sin, cos, tan. There's my sine, cosine, tangent. But you'll notice in little yellow writing above each of these buttons, you'll see sine -1, cosine -1, tan -1. These right here are the inverse functions. And again, the useful thing here is that it's just a series of buttons on my calculator. In this case, since it's written in yellow on mine, it might be secondary function on yours as well. I'm going to have to push the shift button and then that inverse sine or inverse cosine or inverse tangent in order to use it on my calculator. Just be aware that on your scientific calculator, it may be a different combination of buttons. Okay, but that intro right there is just a really important thing, really important background as to how we can use trig in reverse or inverse, to use the language here, so that I can backtrack and find an angle measurement that creates the given ratio. Well, let's see this in practice. We'll do a couple of problems for today's lesson that involve using this inverse ratio, and then we'll save the rest for the next recording. Okay, so our first example today, you'll see your first couple problems that give you this situation. Let angle A and angle B be acute angles. So let's stop right there. Just that first sentence, what that's literally telling us is that these are acute angles. What does that mean? It means they're less than 90 degrees. The important function there for us is that in a given right triangle, only two of the angles are what we call acute. They're less than 90 degrees. There is exactly one right angle. This is not an acute angle. It's a right angle. Acute angles are less than 90. This one is 90, so this one can't be acute. So when it talks about acute angles in a right triangle, it's talking about the other two guys. As I said in the previous lessons, these are the two angles we're going to care about when it comes to trig functions. Sine, cosine, and tangent can only be taken of these two angles. Okay, so again, that's all it's saying in that first sentence. So let angle A and angle B be acute angles, basically the two angles we can perform a trig function on. Use a calculator, which quite frankly, we're going to be using a calculator for all this stuff, but use a calculator to find their measures to the nearest tenth. What this is basically asking, and you can see it here in both these examples, you'll see that the unknown in both these equations is actually the angle itself. Okay, so whatever happened with the tangent ratio, and again, tan or TOA for opposite over adjacent, whatever opposite over adjacent reduced to, it came out to 0.75. And so what this will end up answering when we solve it is what angle measurement creates a tangent ratio of 0.75. In part B, it's the same kind of question. It's just with a sine ratio, sine or SOHCAHTOA. This would be an opposite over hypotenuse ratio. Whatever that reduced down to or divided into, we got a 0.87 result. What this is going to be answering is what angle measure creates an opposite over hypotenuse ratio of 0.87. So in both cases, we're actually going to be getting a degree measure result. So let's see how that is written out really briefly on the whiteboard, just so we can kind of see it done. So both of them are pretty quick. First one, part A, tangent of angle A is equal to 0.75. Okay, to make this a little bit more simply understood in terms of an algebraic concept, essentially my job here is to solve for A. Okay, 0.75 is a real number. There's nothing to do with that over there. Tangent is an actual function. It's going to do something to A. And so from an algebraic inverse operation standpoint, I need to get the tangent over on this side And so that's where we intro the concept of an inverse trig ratio. So how do I get rid of tangent and move it over here? This is where I'm going to be applying the inverse tangent. So it's the inverse tangent of both sides. It will just happen to cancel out what's here on the left, and I'll be left with just A. So ultimately, I'll get some measurement of angle A, to be a little more specific, just to use that notation. And then what am I taking the inverse tangent of? Whatever's on the other side, in this case, 0.75. And yes, this looks a little scary right now, but here's the good news. This is literally a series of buttons on your calculator. So that on my calculator, as I work through this, what I'm going to be doing is I'm going to first input what's on the inside of the parentheses, basically what I'm taking this inverse trig ratio of. So I'm going to start with 0.75. Okay, there's my 0.75. Now, if I was just taking the tangent, I would just simply hit the tan button on my calculator. But again, I'm taking the inverse tangent, okay? The inverse tangent, this -1. So that's going to be my secondary function here. So on my calculator, at least, I need to hit the shift button first and then the inverse tangent button. Let's see what happens. I get this decimal result. Comes out to 36.86989, yada, yada, yada. It's another gross decimal, but essentially here's what's happening. Let me round this to the nearest tenth. Measurement of angle A came out to approximately, again, round to the nearest tenth, 36.9. 36.9 what? This is in degrees. I've just discovered an angle measurement. So as you see, that was just literally doing a series of buttons on the calculator. So the actual computation is very, very fast, but understanding the result is equally as important here, right? So when I did this magic series of buttons and this number popped out the other side, what does it mean? We've literally found a degree measurement, about 37 degrees, but again, rounded to the nearest tenth, 36.9 degrees. If I were to take the tangent of this number, let's see what would happen. So 36.9. That 36.9 degrees. If I were to take the tangent of 36.9 degrees, so now in this case, I would hit tan. Let's see what number pops out. 0.7508, yada, yada, yada. Notice that's really close to 0.75. The reason it's not exactly 0.75 is because, again, this number was rounded. And so anyway, what this is essentially doing is it's just a demonstration of how this trig ratio is literally just undoing what this does. And my result when I do an inverse trig ratio is going to be in a degree measurement. This is an actual angle measurement in its given triangle, whatever that triangle may look like. All right, part B is the same thing, just a different trig ratio. Part B here, we're now given the sine of angle B, some other angle. This is not necessarily in the same triangle for the record. This is just a different problem. So sine of B is 0.87. Again, literally breaking down, translating as sine of some angle results in this opposite over hypotenuse, SOHCAHTOA, this opposite over hypotenuse decimal result. So if I wanted to solve for that actual angle B, the way I would do that would be by moving the sine to the other side. Basically, how do I get B by itself? I use the inverse operation, in this case, the inverse sine of both sides. On the left-hand side, I'm going to be left with just B. Now, B, again, is an actual angle measurement, so that's where I use this notation just to let myself know it's the measurement of some angle B. And what am I taking the inverse sine of? That other side, which is a 0.87. Okay, again, nice series of buttons here on my calculator. I would again start with my 0.87. Okay. And that 0.87, I need to take the inverse sine of it. So again, instead of the sin button right here, I'm going to be doing the shift button first to let know I'm doing the secondary function. It spits out this number. So literally my result here is that the measurement of angle B, let's round to the nearest tenth again, is 60.5. Now 60.5 what does this actually translate as? This is an angle measurement. So the measurement of angle B is 60.5 degrees. And again, if I want to undo that, now I'll leave this as like it's long, complicated decimal. If I wanted to say take the sine of this angle, I should get a opposite over hypotenuse result. So if I take the sine of this, look what number pops back out the other side, 0.87. So again, these first couple problems are essentially just an illustration of like, all right, here's how the inverse function works. This is what it does or undoes. And the punchline here to understand is that my result of taking an inverse trig operation when I do this inverse operation, I'm going to get a degree measurement result for an angle. Okay, so now let's actually apply this to a triangle. So there's one more example, and I'll go ahead and just stay on the whiteboard here so we can just see it illustrated. Again, we'll see some right triangle, not unlike everything else so far in this chapter. Some right triangle, and this time I'll give it some labels. Let's call it triangle FED. And in this case, I'll actually give you the lengths of all three sides. Now, in case you're wondering, this is actually a Pythagorean triple to reference something from section 1. All three sides are whole numbers. You could test to see if this is in fact a Pythagorean triple by doing an a squared plus b squared equals c squared result. It would check out. That's not what the question is asking here. What the question is actually asking is to find the measurement of angle F. Find the measurement of angle F. So up until this point, up until this section actually of even being aware of inverse trig operations, the only way we'd be able to know anything about these two angles is if we knew the other one, because then we could use triangle sum theorem to kind of figure out, well, the total has to be 180 and inside. I already know this guy's 90. I would need to know one other one so I could figure out what's left over for the third angle. But notice there's no information given here. So this is the first opportunity we'll actually have to figure out what these angles are besides pulling out a protractor and actually physically measuring them. And this, again, is kind of a very common scenario in the real world. Maybe I know, like, this is like a frame of a roof or something like that, or a flagpole and shadow or something like that. And I can actually measure with the, meter stick, measuring tape, laser, whatever it might be. I can measure these distances easily enough. But maybe it's important to me to figure out what angle this is creating, okay, for whatever reason. Again, a reason doesn't pop in my mind right now, but rest assured there are reasons to need this angle. Okay, well, if I need to find this angle, here's where, again, I can use a trig ratio. So it actually does not matter which trig ratio I use. I could actually create a trig ratio with sine, cosine, or tangent, so use what's most comfortable for you. For the sake of this example, I'll use the one from section 4, tangent. All right, again, it did not matter. There's one that exists for all these. Well, tangent of angle F is going to be result. Tan is TOA, SOHCAHTOA, is going to be opposite over hypotenuse. Sorry, totally messed it up. Tangent is opposite over adjacent, TOA. That's why the acronym comes in handy. So opposite over adjacent. Well, there's angle F. Opposite is the 5. That's going to be my numerator. And then adjacent to angle F is this 12. That's the denominator. So whatever the tangent of this angle is, and again, there's some degree measurement there. It does exist. If I take the tangent of it, it must reduce down to 5 over 12. And again, I can figure out that decimal by plugging in a calculator if I needed to. Okay, but in this case, I need to actually solve for angle F. So how do I get this tangent to the other side? This is just like we did in the last example. In this case, now I'm using the inverse trig ratio. So in this case, now I'm going to be taking the inverse tangent of the other side being this 5/12. And that's okay. This is just a division problem. I can do that in a calculator as well. And then all this mess that I've just done by moving the tangent to the other side is going to result in the measurement of that angle F. Now, be careful here. If you had used sine or cosine, you'll end up with a different ratio depending on those, opposite over hypotenuse or adjacent over hypotenuse. It really depends on which trig ratio you use. I use tangent, so this is the result I got. Okay, and rest assured also that if you would use the sine or cosine, you'll see this in my solutions on Google Classroom. I've done all three, and you can see you get the same result for any of the three. But let's explore it with tangent. So in this case, this is literally something, everything over here can be done on a calculator. This is just 5 divided by 12. Whatever that results in, with a series of buttons, I can do the inverse tangent of it, and then that will result in some angle measurement for angle F. Well, let's see this done. So again, first thing I'm going to do is figure out this stuff. So I'll do 5 divided by 12. Ugh, gross decimal, but there it is. Okay, now if I take the inverse tangent of it, literally on my calculator, and all I have to do is hit the shift and then tangent button to see what happens. Okay, so shift, tangent. Okay, so this number, this other gross decimal, let's round it to the nearest tenth, tells us that the measurement of angle F is approximately 22.6 degrees. Done. Again, had you used inverse sine for opposite over hypotenuse or inverse cosine with adjacent over hypotenuse, you would have gotten to the same exact result. And just to prove to you that this is correct, if I were to take the tangent of this degree, I get this crazy decimal. So just bear this in mind right now. If I were to do 5 divided by 12, I get this decimal back. So let me do that really quickly. 5 divided by 12. Hey, there's that decimal. So anyway, that is our introduction to inverse trig ratios. For tomorrow's recording, we'll actually put this into practice with solving an entire right triangle in the fact that we'll be given a right triangle with limited information, and this will pop up where I'm going to be asked to find some missing angle. This is just a dedicated version of that, like, hey, find this angle. In solving triangles, we'll be finding every measurable aspect. But that will conclude today's recording. I'll go ahead and stop the recording right there.